Astro 4, we're live from Cleveland. The most basic information that we would plot, so we'll put that on the vertical axis, is the intrinsic luminosity. I'm sorry, it's called luminosity. That means power, and power means rate of energy, energy per unit time. And we did typical usual units that we would in every day measure power would be watts. Of course, when we're talking about stars, we're immediately going to start switching into scientific notation because the numbers, for example, and everybody knows what a 100-watt light bulb is. That's what I got shining on me right now. Well, the intrinsic luminosities or power of stars, such as the sun, are just mind-bogglingly larger, and we calculated that, right? 4 times 10 to the 26 watts. Just outrageous. But anyway, on this scale here, just to be lazy, we plotted everything. These are powers of 10 or a logarithmic scale because there's such a wide range of power coming from all these different stars. Every one of these little crosses here is supposed to represent some star that's been observed near the sun, maybe in the neighborhood. And except everything has been normalized to the sun's luminosity. That's the one that will scale all other stars to. So on the vertical axis here, we have, well, let's see, a star like the sun would be, do you see my arrow? It'd be right here. And of course, there are stars that are 10 or, gosh, it's hard to read these things. Anyway, I think that's 10, 100, or even 1,000 times more luminous than the sun. And there's lots of stars that are 1/10 or 1/100th the power of. What's the other axis? How would you estimate fairly accurately the surface temperature of a star? A spectrum, remember, that's the light that you would see from an object such as a star spread out into all of its wavelengths, or colloquially, its colors. Or if you're thinking about electromagnetic radiation, you could say technically we're spreading it out into all the different frequencies of photons. And that gives us basic information about any star that we look at. We basically looked at the absorption lines that were present in the star when we took a spectrum. Those are produced by the cooler gases in the upper atmosphere of the star that absorbs the light coming from the inside of the star and leaves a fingerprint in the spectrum of the star. That tells us exactly what kind of atoms are present, what the conditions are in the atmosphere of the star. If you were lazy, and sometimes people do this, sometimes I even do it, the peak power of a black body, so that's basically the wavelength that most of the light's coming out, is just going to be an inverse function of the temperature. So the hotter the surface is, the bluer the star is going to look. And I'm not sure I mentioned this last time, but if you look through a big telescope, as I have done when we were just killing some time on a cloudy night, it's looking at a bunch of stars with a 60-inch telescope. So there's a lot of light. You don't even have to hardly be dark adapted. You can really use your color vision. You can actually see the differences in colors of stars, even by, I'm going to say, maybe just several hundred degrees. You can, and I was practicing a bit. You could get pretty good, telling the difference between a star that's the temperature of the sun. That looks very white. That would be about 5,800 degrees, and that certainly looks different from, say, a star that's 6,500 degrees. It's beginning to look a little bit bluish. Or a star that's 5,000 degrees looks a little bit sort of more reddish or yellow-orange compared to the sun. Anyway, so if you're lazy, you could just plot on this axis here the color of the star, with the red stars being over here and the blue stars being over here. But anyway, the way I plotted it here has the most information. So this, for historical reasons, which you don't need to care about, it's really just a luminosity temperature plot for stars, but historically it's called the Hertzsprung-Russell diagram because those two astronomers first plotted this. And they could plot it as soon as people really were able to know what property of stars. If you want to know their power, you have to know their distance. So there were big surveys using the parallax method, which was also covered at the end of last lecture. And the final thing that I showed you then is there's a striking correlation for most stars. Maybe this shouldn't surprise you, that the more intrinsically powerful the star is, you could call it brighter, but brighter depends on whether it's near or far. But I'm saying intrinsically, the more powerful stars also have hotter surface temperatures. They're bluer. And that kind of makes sense if you think about what we learned from Stefan's law of black bodies, because stars are approximately black bodies. The power per unit surface area of a black body like a star is going to be proportional, of course, to this is per unit surface area. It's going to be proportional to the fourth power of the surface of the star. So yes, of course, stars that have hotter surfaces, each square meter of that star is putting out much, much more power than a cooler star. And so even if all of these stars have about the same size, they have about the same diameter, approximately, about the same surface area. So they have about the same number of square meters. It's just that these hot blue stars here are so much better at putting out power with each square meter they got. These square meters of these very reddish cold stars just don't put out much power at all. But the interesting question that came up perhaps in your mind on Wednesday that I want to answer today, and I'm just going to sort of spill the beans and tell you the answer up front and then explain why. Okay, I got that you can have hot stars that should be more powerful and cool stars that should be dimmer. What I don't got is how come there's such an incredibly wide range of power found among different kinds of stars? How come the galaxy has such a wide range of stars? You know, they range over a factor of 10 in temperature. And so, of course, temperature to the fourth power, that would be a range of 10,000. Even if they were all the same size, they would still have an range of 10,000 in power. The sun being just a sort of an average mediocre value. Like I said, you can find stars hundreds or thousands of times more powerful than the sun. They're very rare, but they're kind of hard to miss. Or you could find stars which are terribly numerous if you look hard, which are much less luminous than the sun. By the way, anybody want to guess like how far down this goes here? I don't seem to have any crosses that are much less than, I don't know, about a thousandth the power of the sun. It wouldn't be a star anymore. It would just be a kind of a big old planet. And that is one other thing that you could study in more detail if you took Astro 3. But the reason that stars have such different intrinsic power to them, it all depends on one thing, which we haven't seen yet in the star, because you have to dig a little bit. It depends on what's going on in the center of the star, because that's where all the energy is produced. And that conditions there depend on one thing about the star. Really, just this is amazing. Just one simple thing, which is how much mass does the star have? Mass determines pretty much everything you want to know about a star. This is kind of surprising how simple they are. Certainly for the purpose of Astro 4, but even, for pretty sophisticated astronomy, I don't really need to know too much more about a star once I know its mass, because that's going to tell me how much power is coming out, and then it's going to tell me what its size is and its surface temperature. Pretty much it's going to tell me most of what I could observe on the outside. In fact, it even tells me information about what it would be like inside the center of the star, even though I'm never going to go there. So here's the problem, though. Wouldn't we love to be able to weigh stars? We'd like to know what the masses of stars are, but in general, that is really difficult. What are you going to do? Put it on a bathroom scale? We can't go there. We're very far away. The only star that's close enough to do anything easy with, so the one we know really well, is what? Our own star and our own solar system. How come we know what the mass of the sun is to extremely high accuracy? Because we've been watching lots and lots of objects orbit around its gravity, and they're all obeying all of those Newton's laws of gravity and Kepler's laws of orbits, which are really just explained by Newton's law of gravity. So as a general rule, and by the way, I'm not just talking about masses of the stars, measuring the mass of anything that's interesting in the universe, and I'm very interested in that question. I'm interested in mass of galaxies, clusters of galaxies. I'm interested in the mass of the universe. We're going to get into all of those further down in this course, and they all have the same issue. You need to see, you're really trying to measure the gravity of those objects. How you can't see it, how are you going to do it? You need to see the effects of the gravity accelerating something else. So that's going to tell you how much gravitational force there is. That tells you the mass. So there has to be something else that you could see that's going to be moving nearby, preferably going around in an orbit. And for our purposes, it would be fairly convenient and it's not too unusual going around roughly in a circular orbit, but that's a detail. Maybe you could be going around an elliptical orbit. And so the key, if I want to know how the masses of a lot of stars compare, I'm going to have to find special stars which are in binary star systems. That's pretty much the only way to do this. Aha. So that sounds daunting, doesn't it? Ooh, there's a good word. And I'll show you a little of daunt here. Here's an example where you can see there's two stars. And this is a famous example because one of these stars is the brightest visible star in the sky. Everybody's seen it a million times. It's called Sirius A. Seriously, guys. So here's a series of serious photographs. Seriously. All right, enough of that. Now, this is a very overexposed photograph, actually. So Sirius A is really thousands of times brighter, but it's got a little companion here, this little faint thing, which is called B. You can't see that even without, a decent size telescope. So normally you just see mostly the light from the bright one. But anyway, you get a decent sized telescope, you take a series of photographs or images and have a little bit of patience. I do not recommend this like for a graduate student PhD dissertation, because you'd be getting to be a pretty old graduate student by the time you actually saw these two stars making an orbit around each other. Gosh, okay, you can see it's not a circular orbit because they have a close passage here in 1935, and by 1970, they were further 60, they were further apart. I don't know exactly where they are now in 2023. But what's really happening here is you have two stars which are both experiencing what? The gravitational pull of the other star. So we know, of course, that the force of gravity of A on B is related to the force of B gravitationally pulling on A. And Newton told us what that is. The force of B on A, how's that related to the force of A on B? Equal and opposite. Both of the stars happen to have the same mass, then they would both have this, they're experiencing the same force in opposite direction. So they would both have the same acceleration and they would both be going around in the same orbit. That's not general, that would be a simple case. That's not generally what we see. Usually the brighter one is more massive. We could apply Kepler's third law basically as interpreted by Newton. This is that long, complicated form. So we have the famous proportionality between the cube of the size of the orbit. This is the major axis. So for a circle, that's just r. R cubed is proportional to the square of the period of the orbit. There's some geometric constants, and it's divided by the gravitational Newton constant times the sum of the two masses. So you can see right away here, all we have to do then with this visual binary is we see how long it takes to go around once, how many years. We see what the separation of the stars is. Technically, I'm going to be a little technical here. The two stars aren't exactly going around each other. See my fingers like that? They're not going around each other. Ooh, what a fascinating demo here. They're going around the center of mass. The center of mass could be a little on my nose here. See? They're both going around their mutual center of mass. And so if you know how big the orbits are of these stars, then you've basically got the mass of the star. Lots of stars. I didn't realize this as a grad student. Lots of stars are in binary systems, more than we imagine. In fact, I would say it's probably almost the most common situation for star. You go look at most of the stars in the Milky Way galaxy, it's about a 50-50 chance it has a binary companion to it. Wow, isn't that amazing? The sun, is that a binary? No. Sun is a single isolated star, which is probably good for us. But it's not that far away because the sun has a what? substellar but fairly massive companion, namely Jupiter. All right, that's only what, about 1/300th of the sun's mass, but still, if Jupiter were a bit bigger, as we will see later, hopefully in this lecture, that we would be in a binary star system with a fairly extreme mass ratio. So it's interesting. Something about when stars form, it seems like not all the material often always manages to fall down right onto one star. There's a certain amount of spin or angular momentum there, which is conserved. And so some of the angular momentum flies off and goes often to making a second or even a third object. There's triple star systems too. Ooh, that's more complicated to study. Not going to study that in this class. But let's look back at the binaries. I think I just said this, but here's a nice slide. These drawings are always better than I can do with my nose here, although that was pretty cool. These kids are supposed to be two equally massed stars. Okay, so I guess they sort of look like it here. And they're on a seesaw, and the seesaw, of course, will only be in balance if the center of mass of this whole system is sitting right on the pole of the seesaw. So since these kids are equally heavy, then they have to be an equal distance away from the center of mass. So if this would be a very simple, suppose they're going in orbit, they would both be going maybe in circles of equal size and equal radius around the center of mass. Now here is a more complicated and more realistic situation. We've got twice as much mass in this star. So this is the twins. This is a heavy star, and this is a lighter star here. The heavy star is only half as far away from the center of mass as the light star. The light star is going to get accelerated twice as much as the heavy star. Equal force, but the small object gets accelerated more. So we kind of drilled that into you the first week with Newton's laws. So this one is going to have a much higher orbital velocity than the massive star. Again, with my little nose thing, animation, here's the massive star, here's the light star. Woo! See, they're always on opposite sides. The light one goes in a big circle fast, and the massive one just goes in a small circle. Of course, what's the extreme case of that, where you have a really massive object and just a little light thing orbiting, and they go around the center of mass? The most extreme case of that, I guess, would be a star and a little planet, exoplanet. Because yes, I mean, Jupiter actually does cause the sun to move around a little bit. This would be very important if we wanted to find planets around other stars. Everything in the solar system does not exactly go around the sun. It goes around the center of mass of the solar system. Well, where is the center of mass of our solar system? It's got to be pretty darn close to the center of the sun, because that's so massive compared to everything else. You want to know really where the center of mass of our solar system is? It's inside the sun, but not at the center. It's sort of whichever direction of the sun is kind of pointing towards Jupiter. It's shifted up a little bit there, and a little bit more shift whatever direction Saturn is. So it's somewhere down there, 100,000 miles beneath the solar surface. Anyway, you don't need to know that, but it's enough to make the sun wobble back and forth. It's wobbling back and forth, I guess, every 5 or 6 years because of Jupiter's pull, and it also has an additional wobble every 10 years from Saturn's pull, and we've detected that now in other systems where you can only see the star. About to get to that. That's kind of amazing. So here's the fun part then. What if you didn't have the advantage of Sirius, where it's a nice, well-resolved, bright system? You can see two stars, they're separate. You see that it's a visual binary. What if you didn't have that advantage because it's far away and they're close together? How would you know it's a binary star? Unless you have a special super high magnification telescope, which might be difficult to do or impossible. It looks like one blur of light. It's two blurs of light on top of each other. How would you know there's two stars there? You could look carefully at the spectrum, and if there really were two stars there, and I can prove this to you, you can see it, then what would you see when you look at the absorption lines from the stars? Remember, you have a sort of a rainbow of light. The continuum here is coming from both stars, star A and star B. But superposed on this continuum, if you remember from Wednesday lecture, there's also a distinctive fingerprint series of dark absorption lines here, and the two different stars will each produce absorption lines, but they have different Doppler shifts, right? One of the stars at any one time would be coming towards us at the same time the other star be coming away. So when you look at what you might have naively thought is the spectrum of a single star, you might see a slightly blue shifted set of absorptions and a separate set of slightly red shifted absorptions at the same time. Okay, the star isn't obviously coming and going at the same time. You're looking at the light from two different stars, which are coming and going. They just go back and forth like that. And that is how most binary stars are measured. You can measure very accurately the amount of the red shift or the blue shift, and that how much the wavelength is shifted. So that fractional shift tells us what fraction of the speed of light the star is moving towards us away from us. That is the Doppler effect. So the Doppler effect is beautiful for binary stars. It'll tell us how fast they're moving. We can see how long it takes for them to take one cycle. So we could basically figure out what the mass of the stars is using the Kepler's laws, Newton's law of gravity, like I said before. So that works great, of course, if you measure when the star's coming at you at maximum speed, you get maximum blue shift, then you get maximum red shift. Maximum blue shift is going to work great. It's perfect. I'm looking at you, right? And the stars are like this. Oh, that's nice. They're coming and going towards you. What about another situation, though? Remember, you can't see the individual stars. What if they're going like this, sideways? They're never getting closer or further away to you. The orbit is in the plane of the sky. They're moving the same speed, but it's all sideways. Is there going to be any Doppler shift at all? No. The only way that this method, darn it, this Doppler method is only going to work is if you know that which way the orbit is tilted, which you don't, because you don't have a high magnification telescope. It just looks like one whole blur of light. So what you really want is you'd like to be confident, okay, I can't do this for most binary star systems because they don't really care where the Earth is. They're not all pointing towards the Earth. But if I could find a system that had its orbit exactly edge on, so it was exactly lined up with the direction towards the Earth, then I wouldn't have to worry about this effect at all. What you see would be what you get. I'd be measuring the whole Doppler shift. I certainly want to stay away from any stars that are moving sideways in the plane of the sky because I won't see any Doppler shifts at all. If only I could find some special cases where there's a binary star which has a particular inclination which is viewed edge on. That would be wonderful, wouldn't it? Anyway, that was the diversion on this slide. Could that actually happen in real life? Could we be so lucky? Oh my gosh, yes. There is one super lucky case. This is like a gift that the heavens give us occasionally. Occasionally, you're looking at a star, you don't really notice much of anything special about it, except you might notice that there are two sets of absorption lines getting red shifted and blue shifted and red shifted, but that's all you know. Then, remarkably, at one particular time while you're watching, you need to watch these things maybe for days or weeks or whatever, the light of the star, the brightness dims. It dips down and then it comes back up. And then if you wait more time, it dims again, maybe by a different amount. So what are you seeing here? The dimming is coming about because these stars are moving exactly in an edge-on orbit. It's perfectly inclined to our line of sight. So one star will, once every orbit, one star will get in front of the other star and block its light. And then half an orbit later, the other star will be blocking the light from that star. And so when you're blocking it, you don't see it. So the total amount of light gets dimmer. This is amazing. First of all, it tells you that this is a binary. Then you can use Kepler's laws, Doppler shifts, all that stuff works great. You don't have to worry about geometry, inclination angles. Also, you measure how long the eclipse lasts. Now, you know how fast these stars are moving. So does the eclipse last for a few minutes? Does it last for a few hours? Whatever. You know how fast they're moving. It tells you how big the stars are. I love this. Eclipsing binary stars tells you everything you want to know. It tells you the masses of both stars, and it tells you the sizes, the radiuses of both stars. And I have to put a little shout out here because this method was really pioneered to extraordinary effect by a colleague of mine at UCLA, Dan Popper, who was the world's leading expert on eclipsing binaries. I sort of told you the answer, but I have not told you why. I said, yes, the mass of the star, which we now know how you can measure these quite accurately if you just want to work hard. You're still going to have the question, okay, Matt, why is the mass so important at controlling everything else about the star? What's the mechanism? What keeps stars stable? Or to make this question a little more dramatic, because people I got to make it personal to you. What keeps our sun, that's one you care about, stable? I have to consider the situation. The sun is ridiculously massive. Compare the sun's size, okay, to the Earth. It's much bigger. But then you compare its mass to the Earth's, it's way bigger. You could compare m over r squared for the sun to m over r squared for the Earth. You'd be comparing the surface gravities. How much would you weigh if you could stand? You can't. If you could hover above the surface of the sun, I'll bet you'd weigh a lot more than you do here, wouldn't you? What is it, about 20 times more? And so the deeper you go, the more weight on top is pushing down on the gas in the middle. So there's already a great deal of gravitational force here. Down here, there's even more weight on top of you and more weight and so on. Why, with all of that weight, doesn't the sun just implode? What is going to stop it from gravity just crushing it down? It wants to pull everything towards the center of mass. Here, that's the center of gravity. There must be some other opposing force that's pushing it out. Don't worry. This is not going to happen. I didn't mean to scare any of you. Oh my gosh, I can't even go home back to the dorm. I think gravity might destroy our sun. Then what are we going to do this weekend? The deeper you go into the sun, the more intense the outward explosive force of pressure is. The gas pressure it builds up higher and higher and higher. Pressure, of course, is a force. It's a force per unit area. Like in a tire, you inflate a tire or something. It's pushing out, and of course, if the rubber isn't strong enough or has a little hole, it'll explode. So gas pressure is always pushing out. By the way, how do you get a really high gas pressure? Two ways. You need to have a high density of gas. Okay, so I told you the pressure is going to build up higher and higher in the center of the sun. That's because the gas is getting denser in the center. And then what's the other thing that increases gas pressure? Remember, gas pressure, I hope you remember this from high school, gas pressure is the effect of random collisions of trillions of atoms or molecules, in the case of air here, bouncing around like little, imaginary, not imaginary, but microscopic billiard balls bouncing around, and they want to bounce around and spread out. And when they run into a surface, they keep bouncing on it. This could be the surface of your tire, and it exerts a force outward. So the faster they're moving, that means it's a high temperature, the more the pressure is going to be. So one thing then I've just told you is the density and temperature of the gas in the sun. I have not been into the middle, but I can tell you it must be much higher than it is on a surface. Remember, the surface was only about 5,800 degrees centigrade. It's going to be way, way hotter in the center to balance the crazy force, not crazy, but very large force of gravity trying to crush it down. This is very common in nature. I told you this. It happens almost all the time. You got big forces, but they usually have an opposing force, and they're usually they're in opposite directions. The force of gravity pushing in on this gas, the force of pressure pushing out on it. Those forces are very frequently exactly offsetting. They're exactly canceling out. They're in equilibrium, which means that nothing is going to move because the net force everywhere here is generally zero for most of the life of the sun, for most of the life of all stars. It's a hydrostatic. It's a beautiful equilibrium. I got you worried that gravity was going to crush the sun. Then I told you, actually, there's so much gas pressure. You might have been thinking, oh my God, like, is the sun, it's so hot in the center. It turns out to be 15 million degrees. Is it just going to explode? Is it going to stay exactly the same, through graduation? Aren't you worried that like one of those forces is going to get a little bit stronger? They're huge forces. What if the gravity gets a little bit stronger on Saturday and starts to win out over the pressure? Yeah, there's an evil civilization of super powerful beings that comes in, and they hate humans. Well, they were going to destroy their sun. They're so evil, and we have the power to squeeze down their sun a little bit. We'll make it like 5% smaller with our tremendous super technology capability, thereby increasing the surface gravity of the sun a little bit to where it's higher force inward than the gas pressure force outward. And more, I can't do a really evil laughter. Won't those humans be sorry? Don't worry, humans. I am Dr. Hydrostatic Equilibrium here. Never fear. The evil aliens plot what will happen when they do this. I'm not worried at all. I know what will happen. The sun will shrink a little bit. The gravity will increase. The force inward will increase. The sun will get denser and hotter inside almost immediately. Well, okay, it goes pretty fast, like years, pretty quick. Probably in less time than these aliens can start to squeeze it. It'll have more pressure, and the pressure, how much is the pressure going to increase? Is it going to increase too much? No, the pressure will only increase by the right amount it needs to balance whatever the gravity is. That's what the pressure does. That's how the star figures out how hot it should be in the center. How much gravity does it have? How does it know how much gravity is? It's a mass. Gm over r squared. The sun's temperature got to stay at about 15 million degrees because that's how much mass it has, and that's how strong gravity is on a ball that's mostly made of hydrogen. This amazing fact explains why those really high mass stars on the upper main sequence aren't really they're 100 times more powerful than the sun. But they're not really all that much bigger than the sun. Even though they have more mass, they're more compressed because they have more gravity. They just run hotter and more compressed. And there's something about a star running hotter that means it generates more light, more power. I wonder what that's. Very dense in the sun. It's amazing. It's a gas. The average density of the sun is not that much higher than the density of water. It's like a few grams per cubic centimeter. Okay, that's actually pretty high considering it's a gas. Like gas around here that I'm breathing is like 1/10,000th of the density of water. But still, it's not crazy dense. But in the center of the sun, where all the pressure has squished things down, it is very dense, like thousands of times the density of water, which is pretty insanely high when you consider it still is a gas. So what is this gas made of that's producing all this power? Well, I don't know, if you were around in the 19th century, you knew that the most powerful reactions for generating light and heat was chemistry, rearranging of the electric bonds between different molecules, particularly hydrocarbons, particularly those wonderful bonds between hydrogen and carbon in things like oil and so on, and coal, which is a bunch of hydrocarbons. That was the best fuel anybody knew about that time. Said, well, don't know exactly, but I'm guessing, what if that sun is like a gigantic, and we know how big it is, huge mass, we know how much mass it is, of hydrocarbon fuel. Maybe it's distilled jet fuel. That has an enormous energy content. Don't ask me exactly how it's burning. That's kind of an embarrassing question because, of course, to burn a hydrocarbon, you also need like oxygen to do it or something else to mix in there to make the chemical reaction. You like form carbon dioxide and things like that, and water. So I am really leaving out all kind of details. But if you didn't know much, you actually might convince yourself that you're right. If the sun really was a ball of, like I said, refined hydrocarbon fuel with that mass, and you set it on fire, it could actually produce the 4 times 10 to 26 watts that you see. If you give me I don't know how you get this, to crush OPEC here, you give me a ball of jet fuel that's that big and set it on fire, provide the oxygen, it will be as bright as the sun. Whoa! That is, of course, a huge amount of hydrocarbon. It will burn out. It makes a spectacular fire for like 20, 50 million years, and then it's done. That's it. It's all turned into ash. It's all like carbon dioxide and water, whatever. Graphite, it's dead. Wait a minute. Around the same time, other scientists in the 19th century were beginning to use the radioactive dating method to look at, it's not a new social app, so they looked at the radioactive decay products in old rocks. Rocks from Greenland are really great. Got some of the oldest rocks there, or rocks from like the Australian desert, really old. You look at things like uranium and different isotopes, and you know their half-life. You see how many half-lives they've been around. Well, they've been around billions of years. So that immediately shoots down the idea that the sun could be fueled by any chemical reactions, because it would have died long ago in the early history of the Earth, and there wouldn't be any life here. We'd all be dead. Now, we wouldn't be talking about this in Astro 4. Instead, what you need is a fuel source, a power supply for the sun, which is much more efficient, can last much, much longer, can last thousands of times longer. It was suspected that you got to go where the money is. You got to go where the forces are the strongest if you want to get the most energy released. And of course, the forces that hold molecules together, they're rather weak forces that hold hydrogens and carbons together in something. They're very far apart. I mean, molecules are big and kind of fluffy. You know where the real strong forces are. The really strong forces are right in the very center of the atom. In fact, where's the really strong forces? In the atomic nucleus. So it's pretty obvious, if you want a big energy source, a big energy release, you need to have something happen, some kind of reaction, not with the molecules, but with the nucleus. And people were already thinking about this, actually. Could we rearrange some fairly simple nuclei, and as a result of the rearrangement, liberate some energy, release some energy? Because that's really what a chemical reaction does, except it liberates a pathetic, teensy little amount of energy compared with all the energy that really potentially might be there. Proud to say this really occurred to astronomers first. I don't think anybody else was thinking about such a crazy thing, but astronomers said, well, actually, we've learned, if you look at the atmosphere of the sun, it's mostly hydrogen. That's the simplest element. So you've got a lot of single protons. Those are atomic nuclei. It's very hot in there, so everything completely ionized. The electrons have been knocked off with collision, so you have electrons flying around freely, and you have protons bouncing around each other. What happens if the protons actually encountered one another at a high speed and got close together? Interesting idea. Let me go further with this. Let's speculate a little bit here, as they did. Let's suppose that maybe through a series of reactions, 4 protons came together. That's interesting because that happens to have near approximately the mass of the next simplest stable nucleus of the element of. I'd have to change two of the protons into neutrons. But go with me for the moment. Suppose that you put the 4 protons together, you change 2 of them to neutrons, you could end up with a helium nucleus. Would that be of any interest? You give me 4 protons, I give you back 1 helium. Could that be of interest? Just look at the numbers, and then I'm going to let you all go. And look at this actually in a periodic table of the elements. A good one gives you the exact masses. This is in atomic mass units, which is pretty close to a proton mass unit. I just looked up, and you can look this up in a table too. Here's the mass of a hydrogen atom. All right, it's pretty close to 1. Look at this. Here's the mass of a helium atom, which is pretty much the mass of a helium nucleus. And you're going, yeah, Matt, I mean, one of them has 1 atomic particle, 1 nuclear particle. The other one has 4, so it's 4 to 1. Duh. End of story? No, look at the decimal places. Hydrogen in atomic mass units is 1.008 atomic mass units. So if I get 4 of those flying around freely together, I start then going into my nuclear reaction with 4.032 atomic mass units. That's not the same as what comes out. What comes out is helium-4, which is 4.002 atomic mass units. Anybody notice the difference here? It's this 3 in the second decimal place. What happened? In this fusion reaction, we fused 4 protons together. We lost 0.03 atomic mass units. We lost 3/4 of 1% of the mass that went in. And you're thinking, well, big deal. Why is Malkan going on about something that's less than 1%? So it was lost. It wasn't lost. That mass was transformed. What can mass transform into? E equals mc. So it's a very small amount of mass, but I'm going to get to multiply that mass times c squared. Does anybody happen to remember what c is? Yeah, that's the speed of light. That's one of the larger numbers I know. Does anybody happen to know what c squared is? That's a really large number. That's one of the biggest numbers we've seen so far in this course. And that's how much pure energy is going to get produced by fusing 4 hydrogens into 1 helium. We'll work out the numbers and see if this is going to save us. We'll see if this can keep us happy and under the sunshine for billions of years, or if it's going to run out soon and we're all going to die. And I'm not going to tell you for the whole weekend. You'll just have to worry about it.